In this video, we're going to be taking a look at variations of full-range projectile problems. If you've worked out a full-range projectile problem before, a lot of them are really similar, but once some kind of variation is made to it, it can change the whole process in which you take to solve for your final answer. So in this video, we're going to be taking a look at 4 different scenarios: the elevated launch, launching up to an elevated position, clearing a certain obstacle along the way, and then finding the actual velocity of the projectile at a certain point in time. So at the beginning of each of these projectile problems, a lot of them look pretty similar. You'll have a starting velocity, you'll be given an angle, you typically use cosine for the x component, and then you're going to use the sine function for the y component. And if you were to do those steps, you would get 8.66 meters per second for the y component, and then 5 meters per second for the x component. Now, just like every problem, what you want to start off with is an x and y column to make sure you have all of your known variables and unknown variables organized into 2 columns. So we want to make sure we place our velocity of 5 meters per second in our x column, and then in our y column we have an initial velocity of 8.66 meters per second and acceleration of negative 9.8 meters per second squared. And then if it were a full range problem to where it's going all the way back down to ground level, you would have a final velocity of negative 8.66 meters per second. But since we're looking at variations of the full range problem, we're not going to add that final velocity for now. Okay, so for the first one, what we're going to do is take a look at an elevated launch. So typically, if you're solving for the time of a projectile, you would use that final velocity of negative 8.66 and the initial velocity of 8.66 and the negative 9.8 meters per second squared, and then you could plug it into formula number 1 to solve for time. Okay. If you're working with an elevated launch, you won't be able to do that. What you would do is, if you had an elevated launch, the variable that you would use is a delta y value of negative 2. The reason why you use a delta y value of negative 2 because the object is being displaced 2 meters below its original position when it eventually lands. And then what you would do from there is you would use formula number 2, and you would put the negative 2 in for the delta y. You would still be able to use your VI of 8.66 meters per second. You would have t as your unknown, and then you would have the negative 9.8 meters per second squared there. Now, once you plug everything into formula number 2, you will have a quadratic from there. So you could either 1, use the quadratic formula, or 2, you can also graph it and see the points of intersection with the x-axis for your answers. Now, when you get those different answers, you're going to get 1 negative answer and 1 positive answer. And then the positive answer is going to be your correct answer. So once you use the quadratic formula, plug everything in, you would eventually get a time of 1.97 seconds. Okay. Also, if you have a fairly advanced calculator like a TI-89 or a higher model, you can always use the solve function, plug everything in, and then it'll spit out your answers for you. So that pretty much covers our elevated launch type problem. With that time, you can solve for a bunch of different things, such as the delta x or the final velocity. For the second variation, it says launched to an elevated position. So for this example, it's actually going to be pretty similar to the first one, except the first one, it has a delta y of negative 2. For this one, it's going to have a delta y of positive 2. Because now you're being displaced 2 meters above your original position. So all the steps that I discussed earlier are going to be the same, except you'd have a positive 2. Now this time around, when you use the quadratic formula, you're going to actually get 2 positive answers. The reason for that is because as the projectile rises and falls, it's going to be displaced 2 meters off the ground once as it's rising and then once as it's falling. So this time around, you're actually going to get two positive answers that you could potentially use based on the problem you're solving. And then you would get a time of 0.27 seconds as it's rising to that 2 meters. And then you would get a second time of 1.49 seconds as it's falling to 2 meters. Okay, and then from there you can solve for a bunch of different things with those times. Okay, number 3. Will it clear a certain obstacle? So for questions like this, you would typically get some kind of delta x and a delta y. It would say something along the lines of, will it clear an obstacle that is 10 meters tall, that is 5 meters away? Okay, in this case, you have a delta x to work with, so you can go ahead and use delta x over t equals v, and then you can work on this side of your column. And if they give you some kind of delta x, you can go ahead and put that in. For the example I made, it's 5 meters. And then you can go ahead and use the velocity that you have in your x column, and then you can solve for a time. Okay. Now this one, the time is going to come out to a nice even 1 second on the dot. And then with that time, what you can do is you can take that time, you can plug it into formula number 2 to see if it clears that 10 meter obstacle. You would use the VI that you have over here in this column. You would use the time that you solve for over here. You would still use the negative 9.8 meters per second squared. And again, you would plug in that same t for the t squared at the very end, and then see how your delta y compares to the obstacle that is placed in the problem. The only other scenario where they wouldn't maybe give you a delta x is if they said, will this projectile clear an obstacle at the peak of its flight? Now, if they give you a scenario like that, instead of giving you a delta x, you would know at the peak of your flight, you know that the VF equals 0 at the peak. Okay, in that case, you can go ahead and use formula number 3, and then you can use 0 for your VF. You would still use the same VI as usual, still use the same acceleration as usual, and then you'd be able to find a delta y. And then once you find that delta y, you see if it's greater or less than the delta y of the obstacle to see if it clears it. Okay, that covers our third variation. And then for the final one, if you're solving for an actual velocity, the actual velocity of the projectile is actually a resultant of your horizontal velocity vector and your vertical velocity vector. So this depends on the question that's being asked of you, but you're going to have to take both of those vectors, connect them together in the tip to tail method, and then solve for the resultant from there. So if you were doing something like that, say for example, you were just finding the very final velocity of the projectile. Now, if it comes all the way back to ground level, that final velocity is negative 8.66 meters per second. Now remember, that's only the vertical component, not considering the horizontal component. Now, so when I'm talking about the actual velocity of the projectile, that's talking about combining those two components. So what you would do in any case, you would take the vertical component and the horizontal component, and then you would find the resultant vector of each of those two. So like I said, what you would do is you would grab the vertical component and the horizontal component, connect them in the tip to tail method, which means that wherever one vector ends, the next one starts. And then you connect a line from the beginning of your first vector to the end of your second vector. And then you would use the Pythagorean theorem to find the hypotenuse of your triangle. And then you would be able to solve for the actual velocity of the projectile. Okay, so that sums up how to do our different variations of full range projectile problems. I hope that was helpful to you. Thank you for watching and listening.